Multiphase flow meter design, selection, installation, and hookup considerations. Multiphase flow meters, MPFMs, are essential in the oil and gas industry for accurately measuring the flow rates of oil, gas, and water in multiphase flow streams. Below are detailed considerations for their design, selection, installation, materials of construction, operability, maintainability, and associated parameters for remote monitoring and calibration. Design and selection considerations. 1. Measurement principles. Venturi-based measures differential pressure to determine flow rates. Gamma densitometry uses gamma rays to measure phase fractions. Electromagnetic measures the conductivity of the fluid to determine phase composition. Impedance-based measures the impedance of the fluid to determine phase fractions. 2. Accuracy and precision. High accuracy. Ensure the flow meter provides accurate measurements across a wide range of flow rates and fluid compositions. High resolution for detecting small changes in flow rates and phase fractions. 3. Rangeability. Wide operating range, capable of measuring low to high flow rates accurately. Dynamic range, suitable for varying flow conditions typically encountered in upstream operations. 4. Response time. Fast response quickly adapts to changes in flow conditions to provide real-time data. 5. Integration with control systems. DCS SCADA compatibility. Ensure compatibility with distributed control systems, DCS, and supervisory control and data acquisition systems for remote monitoring and control. Installation and hookup considerations. 1. Location. Optimal positioning. Install at locations where flow conditions are stable and representative of the overall flow stream. Straight pipe requirements. Ensure sufficient upstream and downstream straight pipe lengths to minimize flow disturbances. 2. Orientation. Vertical or horizontal. Select appropriate orientation based on the flow meter design and installation guidelines. Ensure the flow meter is installed in the correct flow direction as specified by the manufacturer. 3. Accessibility. Maintenance access. Install in locations that are easily accessible for maintenance and calibration. Space requirements. Ensure adequate space for installation and removal of the flow meter and associated equipment. 4. Supports and anchoring. Vibration minimization. Properly support and anchor the flow meter to minimize vibrations and ensure stable operation. Structural integrity. Ensure the installation structure can support the weight and operational forces of the flow meter. Materials of construction. 1. Body and housing. Stainless steel, commonly used for its corrosion resistance and strength. Duplex stainless steel offers higher strength and corrosion resistance for more demanding environments. Inconel Hastalloy high corrosion resistance for sour service and highly corrosive fluids. 2. Internal components. Non-corrosive materials use materials that resist corrosion and wear, such as ceramic or coated metals. Seals and gaskets. Select materials that withstand the operating temperatures and pressures, such as Viton or PTFE. Operability and maintainability. 1. Ease of operation. User-friendly interface. Ensure the flow meter has an intuitive interface for operators. Remote monitoring. Capability to monitor and control the flow meter remotely via DCS SCADA systems. 2. Maintenance. Self-diagnostics. Flow meters with built-in self-diagnostics to alert operators of potential issues. Modular design. Components that are easy to replace and service to minimize downtime. Calibration. Procedures for easy and accurate calibration in the field. 3. Durability. Long service life. Components designed for long-term durability under harsh operating conditions. Corrosion and erosion resistance. Use materials and coatings that extend the lifespan of the flow meter. Associated parameters on DCS for remote monitoring. 1. Flow rates. Oil flow rate, real-time measurement of the oil phase flow rate. Gas flow rate, real-time measurement of the gas phase flow rate. Water flow rate, real-time measurement of the water phase flow rate. 2. Phase fractions. Oil fraction, proportion of oil in the multiphase flow. Gas fraction, proportion of gas in the multiphase flow. Water fraction, proportion of water in the multiphase flow. 3. Pressure and temperature. Inlet pressure, real-time pressure measurement at the flow meter inlet. Outlet pressure, real-time pressure measurement at the flow meter outlet. Temperature, real-time temperature measurement of the flow stream. Number 4, diagnostics and alerts, system health, monitoring of flow meter health and performance. Alerts and alarms, notifications for operational anomalies or maintenance needs. Calibration and remote test capability. 1. Calibration, regular calibration, scheduled calibration to ensure measurement accuracy. In situ calibration, capability to perform calibration without removing the flow meter from the installation. 2. Remote testing, test routines, remote initiation of test routines to verify flow meter performance. Data logging, recording and analysis of test data for performance assessment. MOVs, motor-operated valves for remote operation. 1. Integration with flow meter, automated control, use MOVs for automated control of flow paths based on flow meter data. Feedback loops, real-time adjustments to flow rates based on flow meter measurements. 2. Operational efficiency, remote operation, MOVs can be controlled remotely, reducing the need for manual intervention. Safety, enhanced safety by minimizing personnel exposure to hazardous environments. 3. Maintenance, diagnostics, MOVs with self-diagnostic capabilities to identify and report issues. Redundancy, implement redundancy in critical applications to ensure continuous operation. Practical examples. 1. Offshore production facility. Flow meter type, Venturi-based multiphase flow meter with gamma densitometry. Material, duplex stainless steel for body and housing. Installation, installed vertically with sufficient upstream and downstream straight pipe lengths. Remote monitoring, integrated with DCS for real-time monitoring of oil, gas, and water flow rates. 2. Onshore well testing, flow meter type, impedance-based multiphase flow meter. Material, Inconel for high corrosion resistance. Installation, horizontally installed with robust supports to minimize vibrations. Calibration, in situ calibration capability to ensure measurement accuracy. 3. Subsea application, flow meter, electromagnetic multiphase flow meter. Material, Hastalloy for extreme corrosion resistance. Installation, subsea installation with remote monitoring and control via SCADA. Remote testing, capability to perform remote diagnostics and calibration tests. 4. High-pressure gas lift operations, flow meter type, Venturi-based multiphase flow meter with high-resolution sensors. Material, stainless steel with ceramic internal components for durability. Installation, installed in high-pressure sections with specialized anchors to withstand forces. Maintenance, modular design for easy replacement of worn components. 5. Enhanced oil recovery EOR systems, flow meter type, gamma densitometry-based multiphase flow meter. Material, carbon steel body with protective coatings for specific environments. Installation, positioned for optimal flow measurement with sufficient space for maintenance access. Integration, fully integrated with DCS for automated control and monitoring. By considering these detailed design, selection, installation, and operational criteria, multiphase flow meters can be effectively used to enhance the accuracy, reliability, and efficiency of flow measurement in various oil and gas applications. Advantages of multiphase flow meters at the exit pipeline of every oil well cluster. In onshore oil fields, installing multiphase flow meters, MPFMs, at the exit pipeline of every oil well cluster provides numerous distinct advantages for both the well clusters and the central processing facility. These advantages span from improved monitoring and control to enhanced operational efficiency and safety. Advantages at the well cluster level. 1. Real-time flow measurement, accurate phase monitoring. MPFMs provide real-time measurements of oil, gas, and water phases directly at the exit of each well cluster. Production optimization. Immediate feedback on production rates allows for rapid adjustments to optimize well performance and ensure maximum recovery. 2. Operational efficiency. Reduced need for test separators. By eliminating or reducing reliance on test separators, MPFMs simplify the infrastructure and reduce maintenance. Continuous monitoring. Continuous uninterrupted flow measurements help in identifying and mitigating issues quickly without shutting down the wells for testing. 3. Enhanced data quality. High-frequency data collection. Frequent data collection improves the quality of production data, aiding in more accurate reservoir management and production forecasting. Detailed flow analysis provides detailed insights into well performance, including identifying issues such as water breakthrough, gas coning, or slugging. 4. Improved allocation and accounting. Precise allocation. Accurate phase measurements enable precise allocation of production from each well cluster, ensuring fair and transparent accounting. Regulatory compliance helps in meeting regulatory reporting requirements by providing accurate production data for each well cluster. 5. Enhanced troubleshooting. Rapid issue detection detects anomalies or changes in flow patterns that may indicate well integrity issues or equipment malfunctions. Targeted interventions enables targeted interventions and maintenance, reducing downtime and associated costs. Advantages at the central facility level. 1. Centralized data integration. Aggregated monitoring. Integrating data from all MPFMs at the central facility allows for comprehensive monitoring of the entire field's production. Holistic view. Provides a holistic view of field performance, facilitating better decision-making and field management. 2. Optimized processing. Balanced flow management. Real-time flow data helps in balancing the inflow to the central facility, preventing bottlenecks and optimizing the processing capacity. Improved separation efficiency. Knowing the composition of incoming fluids allows for better tuning of separation processes, improving efficiency and reducing operational costs. 3. Enhanced production planning. Data-driven decisions. Accurate, real-time data supports better production planning and scheduling. Resource allocation. Enables efficient allocation of resources such as chemicals, power, and maintenance personnel based on actual field conditions. 4. Improved reservoir management. Reservoir performance analysis. Detailed phase data supports better analysis of reservoir performance and helps in planning secondary and tertiary recovery methods. Informed drilling decisions. Accurate production data informs decisions about drilling new wells or reworking existing ones. 5. Safety and environmental compliance. Leak detection. Continuous monitoring helps in early detection of leaks or spills, enhancing safety and minimizing environmental impact. Emissions monitoring. Accurate gas measurements assist in monitoring and managing greenhouse gas emissions. Practical examples of usefulness at the central facility. 1. Production balancing. Scenario: the central facility receives varying amounts of oil, gas, and water from different well clusters. Without MPFMs, it's challenging to predict and manage these variations. Benefit: MPFMs provide real-time data, allowing operators to adjust the processing rates and optimize separator performance, ensuring smooth operations and maximizing throughput. 2. Enhanced troubleshooting. Scenario: a sudden drop in oil production is observed at the central facility. Benefit: with MPFMs installed, operators can quickly identify which well cluster is underperforming and take targeted action to address the issue, minimizing downtime and production loss. 3. Accurate allocation. Scenario: production data from several well clusters need to be accurately allocated for revenue distribution and regulatory reporting. Benefit: MPFMs provide precise measurements of each phase from every cluster, ensuring accurate allocation and compliance with regulatory requirements. 4. Optimized chemical injection. The central facility uses chemicals for enhanced oil recovery, EOR, and needs to optimize the injection rates based on incoming flow compositions. Benefit: MPFMs provide real-time data on water cut and gas-oil ratio, allowing for precise control of chemical injection rates, improving EOR efficiency and reducing costs. 5. Maintenance planning. Scenario: the central facility must schedule maintenance without disrupting production. Benefit: MPFMs provide detailed insights into flow patterns and potential issues, enabling predictive maintenance and better scheduling to minimize production impact. Conclusion: installing multiphase flow meters at the exit pipeline of every oil well cluster in onshore oil fields offers distinct advantages in terms of real-time monitoring, operational efficiency, data quality, allocation accuracy, and safety. These benefits extend to the central facility, enhancing overall field management, optimizing processing, improving production planning, and ensuring regulatory compliance. By leveraging the detailed data and insights provided by MPFMs, operators can make informed decisions, quickly address issues, and maximize the efficiency and profitability of their oil and gas operations. Advantages of chemical injection at wells and central facility with multi-phase flow meter implementation. Implementing multi-phase flow meters, MPFMs, at the exit pipeline of every oil well cluster and integrating their data into the central facility offers significant advantages for chemical injection processes, both at the wellhead and at the central processing facility. These advantages improve the efficiency, effectiveness, and cost-effectiveness of chemical injection operations, enhancing overall production performance and reducing operational issues. Advantages of chemical injection at wells. 1. Precision in chemical dosing. Accurate phase measurement. MPFMs provide precise data on the oil, gas, and water fractions, allowing for more accurate dosing of chemicals, such as demulsifiers, scale inhibitors, and corrosion inhibitors. Targeted injection. By understanding the exact composition of the produced fluids, operators can target the injection of chemicals where they are most needed, improving their effectiveness. 2. Enhanced efficiency. Optimized injection rates. Real-time flow data helps in adjusting chemical injection rates dynamically, reducing wastage and ensuring optimal treatment. Cost savings. More accurate dosing and reduced chemical wastage lead to significant cost savings over time. 3. Improved well performance. Prevention of issues. Timely and precise chemical injection helps in preventing common production issues such as scale buildup, corrosion, and emulsions, thereby maintaining well productivity. Increased recovery. Effective chemical treatment can enhance oil recovery rates by maintaining optimal flow conditions within the well. 4. Monitoring and control. Real-time adjustments. Continuous monitoring allows for real-time adjustments to chemical injection programs based on changing flow conditions. Feedback loop. Integration with DCS SCADA systems provides a feedback loop for automated control of chemical injection, improving responsiveness and reducing manual intervention. 5. Environmental compliance. Minimized overuse. Accurate dosing minimizes the overuse of chemicals, reducing the environmental impact of chemical injection processes. Compliance monitoring. Continuous data from MPFMs ensures compliance with environmental regulations regarding chemical use and discharge. Advantages of chemical injection at the central facility. 1. Centralized control. Integrated data. Aggregated data from all well clusters enables centralized control of chemical injection programs across the entire field. Coordinated injection strategies. Allows for coordinated chemical injection strategies that optimize overall field performance, rather than isolated well performance. 2. Efficiency and cost effectiveness. Bulk purchasing and storage. Centralized control can lead to bulk purchasing and storage of chemicals, reducing costs. Optimized distribution. Efficient distribution of chemicals based on real-time needs reduces wastage and ensures that chemicals are used where they are most effective. 3. Enhanced processing efficiency. Optimized separation. Knowing the composition of incoming fluids allows for better tuning of separation processes and targeted chemical treatments to enhance separation efficiency. Improved emulsion breaking. Real-time data on water cut and oil quality aids in adjusting demulsifier dosing to improve emulsion breaking and separation efficiency. 4. Reduced maintenance and downtime. Proactive issue management. Timely chemical treatment helps in preventing issues like scaling and corrosion in pipelines and equipment, reducing maintenance needs and associated downtime. Predictive maintenance. Continuous monitoring and data analysis enable predictive maintenance strategies, scheduling interventions before issues escalate. 5. Enhanced safety and environmental compliance. Safer operations. Proper chemical dosing reduces the risk of corrosion and leaks, enhancing the safety of the central facility operations. Environmental protection. Optimized chemical use minimizes the environmental impact of discharge and complies with regulatory standards. Practical examples of enhanced chemical injection. Wellhead scale inhibition. Scenario: a well cluster produces high levels of water, leading to scale formation in the downhole equipment. Benefit: MPFMs provide real-time data on water cut, enabling precise dosing of scale inhibitors directly at the wellhead. preventing scale formation and maintaining production efficiency. 2. Central facility emulsion treatment. Emulsion issues are affecting the efficiency of oil-water separation at the central facility. Benefit: real-time data from MPFMs across all well clusters allows for optimized dosing of demulsifiers at the central facility, improving separation efficiency and reducing processing costs. Corrosion inhibition in pipelines. Scenario: corrosion due to produced fluids is a concern for the integrity of the gathering pipelines. Benefit: MPFMs provide accurate data on fluid composition, enabling precise dosing of corrosion inhibitors at strategic points, extending the life of the pipelines and reducing maintenance costs. 4. Gas lift optimization. Scenario: gas lift operations require accurate measurement and control of gas and liquid flow rates for optimal performance. Benefit: MPFMs provide precise measurements of gas and liquid phases, allowing for optimized gas injection rates and reducing the amount of gas needed for effective lift, leading to cost savings. 5. Enhanced oil recovery, EOR. Scenario: EOR processes such as polymer flooding or water alternating gas require precise chemical injection to be effective. Benefit: MPFMs provide real-time data on the effectiveness of EOR chemicals, allowing for dynamic adjustments to injection rates, improving the overall recovery rates and efficiency of the EOR process. Conclusion: implementing multiphase flow meters at the exit pipeline of every oil well cluster provides significant advantages for chemical injection processes both at the wellhead and the central facility. These advantages include enhanced precision in chemical dosing, improved operational efficiency, better well and facility performance, and reduced costs. By leveraging the detailed, real-time data provided by MPFMs, operators can optimize chemical injection strategies, enhance production performance, and ensure compliance with environmental and safety regulations.